guys, it's Michelle and welcome to Michelle's STEM Journey. This week's problem of the week comes from the year 2019 10A problem 11 and it deals with factoring. I hope you all enjoyed this video and let's get started. The problem states how many positive integer divisors of 201 to the 9th power are perfect squares or perfect cubes or both. In this problem, we will be needing some factoring rules, and one factoring rule that we'll be needing is a rule that states a to the mth power times b to the mth power equals a times b to the mth power. And so looking back at the question, it states how many positive integer divisors of 201 to the 9th power are there. So basically, we can first start off by factoring 201. So we can already tell that it is not divisible by 2, so let's try 3. And a hack to know whether or not a number is divisible by 3 or not is adding up the digits and seeing if it is a multiple of 3. And so 2 plus 0 plus 1, that gives us 3, and 3 is a multiple of 3. So 201 would be a multiple of 3. And now if you divide 201 by 3, we will get 67. And seeing that 67 is also a prime number, we can stop with the prime factoring. So now we know that 3 times 67 would give us 201. But the question is 201 to the 9th power. So looking back at the factoring rule right here, we see that to satisfy this equation, we will need to make the exponents of 3 and 67 9. In this problem, it is also important to realize that the exponents of 3 and 67 can be any number as long as it is in the range of 0 to 9. So any exponent in the range of 0 to 9 for 3 and 67 will always give you a result that is a factor of 201 to the 9th power. So these are all of the possible combinations, but the thing is, the question is only asking about perfect squares, perfect cubes, or both. So starting off with perfect squares. The exponents of a perfect square must be even, and because the range is 0 to 9, the exponents of 3 and 67 for perfect squares must be either 0, 2, 4, 6, 8. So this would give us the following combinations. So this gives us 5 choices. This would give us 5 choices, so it would give us 5 times 5, which is 25 possible combinations for perfect squares. So we have 25 perfect squares. Now moving on to perfect cubes. Perfect cubes must have multiples of 3 for each of their prime factored exponents. So we have either 0, 3, 6, or 9 for both 3 and 67. And because there are 4 choices for 3 and 4 choices for 67, we would get 4 times 4, which is equal to 16. So 16 perfect cubes. And now we can just add these together. 25 plus 16 gives us 41. However, we do have overcounted powers. Because it is saying or both, that means that the exponent of 0 and 6 occurs in both perfect squares and perfect cubes. And so the combinations with these 2 exponents are overcounted, so we must subtract those. So here is a list of the overcounted powers. So as you can see, there are 4 overcounted combinations, so we must subtract 4 from 41. and this would give us 37. So the answer is C, 37.